Assalamualaikum warahmatullahi wabarakatuh. Now we continue with Maxima and also Minima concept, but this time around it's for more than one independent variables. So in the study of differentiable functions of one variable, let's say we have y as a function of x. Okay, so we only have one independent variable in the previous topics. Then we can have, for instance, if let's say in the form of graph, it looks like this, for instance. Okay, then we can have, let's say, pick one point here, x1, and then we draw a line. That line is a tangent to the curve at point x1. So here we can have maximum point. We may have relative maximum occur at that point. And the line, the straight line here is a tangent line to the curve. Okay, and then it has to be a horizontal line. Alright, but what about if we have, let's say, z as a function of x and y? So in this case, we have two independent variables, namely x and y, and this will give answer to z. Okay, so this can be, visualized in 3 dimensions. Right, now, if we have this kind of 3 dimensions here, so how do we figure out maximum or minimum, relative maxima or relative minima? Alright, so here it is. Let's say if we have a function, call it z as a function of x and y. Okay, let's say if we differentiate z with respect to x and z with respect to y, both of them exist. Okay, if all partial derivatives of x and y exist, z with respect to x, z with respect to y exist, so there must exist horizontal plane tangent. So instead of one tangent line, it becomes a plane, and that plane is horizontal plane tangent to the maximum point or to the minimum point. Alright, and it becomes tangent to the surface of a point in order for the surface to have a relative maximum at that point. Okay, if it is relative maximum, you see the first graph here, A, okay, 14.8 A, then you have maximum point here, and then you see this plane, which is cream color, okay, and the maximum is here, isn't it? So this cream color is a plane, horizontal plane, and then you put it on top of maximum point here. Alright, so it becomes a surface to that maximum point. That surface, this particular point, this particular surface, become a tangent to the maximum point of this graph, 3-dimension graph. But if we talk about relative minima, so you see this surface, okay, plane, it is touching the minimum point, which is here, and it becomes a plane tangent, isn't it, to that relative minimum point here. So this, okay. All right, now, so here, if you find partial derivative of z with respect to x, which this is this, also can be denoted as zx, it must be 0. Same goes to delta z over delta y must be 0. So this one is z, y equal to, alright. So both number 1 and number 2 must be 0 at that particular point. Okay? When I say at that particular point, if we go back this graph, this point or this point. Alright? Now, then that particular point that I showed you earlier is what we call critical points, okay, for the surface. Okay, critical point for the surface. And then, as usual, like one variable case, for more than one independent variable case, we must also have second derivative test. Okay, so the second derivative test that we must have, that must involve, is basically second partial derivatives as well as the value of d at the critical point A and B. We get the value of d. Alright? So, how do we do it? Let's look at this in detail. We need to do tests for maxima and also minima. So let's say we have this function z as a function of x and y. Alright? So if you take partial derivative of z with respect to x, equate it to 0. Take partial derivative of z with respect to y, equate it to 0 at a point, call it point A and B. Alright? And suppose that all second partial derivatives are continuous there. Then we must have d. D is what? D is discriminant. D is given by this formula. You see here the first bit, the second bit, the third bit. The first bit is, second derivative of z with respect to x multiplied by second derivative of z with respect to y minus partial derivative of z with respect to x and then do it with respect to y. Alright, also can be denoted as this symbol. Alright, and then we need to determine the value of d. This one will be shown after this, yeah. But I just want to show you the formula of d or discriminant. Alright, but another way to do this is you can have d in the form of matrices 2 by 2 matrix, and then you have this, and then you have this, and then you have this, and then you have this. Okay, alright, let's go into detail about d here. We need to check d at critical point of A and B, and if d that we have calculated is greater than 0, okay, then we have two possibilities, because now remember, we need to decide whether it's minimum or maximum, the test of maxima and minima. So as long as d here is positive value, then A, zxx greater than 0, alright, and zyy also greater than 0, then we have relative minimum occurs at this particular critical points. But if zxx is less than 0, also zyy is also less than 0, then we have relative maximum. This only if the case is d greater than 0. What if d less than 0? If d is less than 0, we can have neither relative maximum nor relative minimum. At this point, both can exist, and this is what we call saddle point. Saddle point is like you have minimum, and then at the same time at that critical value you have maximum. Okay, but if d is equal to 0, then the test is failed. Then you have to investigate the function near the point, and this one usually we don't request you to do at your level, yeah. So it's either number 1 or number 2. But if it is number 1, you need to decide whether it's relative minimum or maximum. So A, if this occur, relative minimum. If not, then B, relative maximum. Okay. Now let's look at one example. We can have the checking or the test for relative maxima and minima by having these steps of procedure. So let's say we have this function z equal to 4 minus 4x squared minus y squared. And we need to test whether, it has relative maxima or minima. So as usual, we need to find delta z over delta x, partial derivative of z with respect to x, and delta z over delta y, partial derivative of z with respect to y. So delta z over delta x, you see this one becomes 0, this one is not our constant, then becomes 8 minus 8x, which is this. But if it is this one, then you see this one only, isn't it? Delta z over delta y, we have minus 2y, which is this. Okay. Alright. Now, once we have this and this, we need to find x and y. Okay? at this particular point. So when we have minus 8x, we equate it to 0. Okay? We equate it to 0, so it becomes, optimization. So delta z over delta x equal to 8 minus 8x equal to 0. Now we need to find x. What is it? So obviously from here, x is 0. Okay? What about delta z over delta y, which is minus 2y? Equate it to 0. So delta z over delta y equal to minus 2y. Equate it to 0. From here we can get y equivalent to 0 as well, isn't it? So x is 0, y is 0. When x is 0, y is 0, find z. So we know that z is this one. 4 minus 4, 0 square minus 0 square. So 4 minus 0 equal to 4. So here x is 0, y is 0, z is 4. So this is our critical point. And then after that, find all second partial derivative. Differentiate z again with respect to x from here. Okay, from here, don't equate it to 0, yeah? Alright, so here I use eraser. After that, we need to find delta z over delta x. I erase equal to 0 because now I want to find this. But when I want to find this x, of course I need to equate it to 0. Okay, so then I get minus 8, isn't it? Find the second derivative, delta z over delta y. Okay, from 2 minus 2y, you get minus 2. Delta z over delta x, delta y, okay, equals, then you're going to get 0. I hope by now you know how to find this, yeah? Alright, once we get this, we can find discriminant or D. Alright, evaluate D at each critical point. So we have x equal to 0, y equal to 0, z equal to 4, isn't it? So here, we know that the formula A of D is given by this. You just need to plug in the results that you have earlier. So when you plug in, alright, this one is delta z over delta x second time. This one is delta z over delta y the second time. This one is what? This one is basically delta z over delta x delta y, which is 0, isn't it? Okay, then what you get here is 16. 16 is obviously greater than 0. When it is obviously greater than 0, then we can check whether we have relative maxima or minima. But if we have D less than 0, what happens? Saddle point. But if it is equal to 0, remember, then the test is failed. Alright, now let's move on with this example. We know that delta z over delta x for the second time is less than 0. Why? Because the answer is minus 8. This one, minus 2 the answer. So both of them less than 0. When both of them less than 0, relative maximum occur at 0, 0, 0, 0, 4. Okay, so it's going to look like this. Of course, in the exam or in any assignment, I don't ask you to draw this, but this is just for visualization so that you can see what does it mean by relative maximum when D is greater than 0, which is 16. How do we visualize it? So it looks like this basically. Okay, so 0, 0, 4 is here. So you can see clearly it is a relative maximum. Okay. Have the second example. Let's say we have this function z as a function of x and y, but this time around, if you look at the function, it is z equals to y squared minus x squared. So what do we need to do? We need to test z for the relative maxima and minima. We know that if I rewrite again the formula for D, it is second derivative of z with respect to x multiplied by second derivative of z with respect to y minus mixed partial derivative of z with respect to x and also y. And the whole thing here, you square it. Okay, that's the formula. Okay, now, so let's find partial derivative. So we have delta z over delta x, okay, equivalent to minus 2x, isn't it? So if I take the second derivative, delta z over delta x, once again, I'm going to get minus 2, isn't it? Okay, what about, with respect to y? Delta z over delta y, I'm going to get 2y. But if I take the second derivative with respect to y also, I'm going to get positive 2. Okay, what if I take mixed partial derivative, delta z over delta x we already found here, then differentiate again with respect to y. Why do I get 0? But if we differentiate this second time, y delta x, we're going to get 0 also. So these two are the same, isn't it? Okay, so now we can find d. D is actually this one multiplied by this one minus this, isn't it? So here, minus 2 multiplied by 2 minus 0. What do you get? Minus 4. Okay, minus 4 for D is less than 0. Therefore, is neither relative maxima nor relative minima. So this one is what we call saddle point. Okay, if we try to visualize this saddle point in the form of graph, then it may look like this. So this is our z, our x, our y. So you see here, maximum, but at the same time, minimum. So you see the blue one here, it makes it look like a saddle of the horse, isn't it? Okay, now let us move to the next example, which is more realistic one, profit maximization. Adele Lighting manufactures 20-inch lamps and also 31-inch lamps. Suppose that X is the number of thousands of 20-inch lamps, and the demand for this is given by P1 equal to 50 minus X, where P1 is in dollar. Similarly, suppose that Y is the number of thousands of 31-inch lamps, and that the demand for this is given by P2 equals to 60 minus Y, where P2 is also in dollars. Adele Lighting's joint cost function for this lamp, for both, the 20 and also 31-inch lamps, is basically C equivalent to 2XY in thousands of dollars. Therefore, Adele Lighting profit in thousands of dollars is a function of two variables, X and Y, isn't it? So the question here is, we need to determine Adele profit. Alright, now, let's do this, but here I want to do some correction first. If we look at this, we need to correct it. We have to have 2 here, otherwise it's going to be a bit difficult for calculation. Alright, so let's collect all the information, then we proceed to the solution. Okay, so in this case, get some basic idea first. So we have the first information is about the demand for 20-inch lamp. The second information is about the demand for 31-inch lamp. The third information is the joint cost function for both lamps. Okay, the question is asking you to determine maximum profit. But in order to determine maximum profit, we need to know how many X, we need to know how many Y, isn't it? Alright, so let's do it one by one. Because it involves two lamps, Therefore, this is a profit maximization process with two independent variables, namely 20-inch lamps, and the quantity is X, and also 31-inch lamps, and the quantity is Y. Okay. So we know that profit function, in this case denoted as P, is a function of 20-inch lamps and also 31-inch lamps. Profit is actually revenue minus cost, isn't it? In this case, we have two different revenues coming from selling 20-inch lamps and also from selling 31-inch lamps. So we're going to have revenue for 20-inch lamp plus revenue for 31-inch lamp minus the cost of both of them. Alright. Now the revenue for 20-inch lamp is actually price of 20-inch lamp times quantity of 20-inch lamp plus what about revenue of 31-inch lamp? It is price of 31-inch lamps times quantity of 31-inch lamp, which is Y, P2 times Y, minus the cost, okay, the joint cost. So let's make it more specific. Therefore, profit function of selling both types of lamps is actually 50 minus X times X plus 60 minus 2Y times Y minus the joint cost, which is 2XY. In order to maximize profit, we can see here the profit function depends on two independent variables, which are two lamps, X and Y. So in order to maximize profit, we need to find the discriminant. The discriminant formula, we know that it is PXX times PYY minus PXY square, isn't it? In order to maximize profit, D has to be positive. Relative maxima or relative minima, D has to be positive. Okay, now, so how do we do it? That means we need to find Px, we need to find Py, and then we need to find Pxx. We also need to find Pyy, and then we need to find Pxy. Okay, now here Px is actually can also be rewritten as, let me erase this mess first, can also be rewritten as delta P1 over delta X, isn't it? So in this case, we're gonna get 50 minus 2X, isn't it? And then minus 2Y, because we differentiate this with respect to X, we get Y, 2Y, isn't it? For Py, it can also be denoted as the delta P2 delta Y. So we're going to have 60 minus 4Y, isn't it? From here, okay? And then minus 2X. Because it's about maximization a profit, we need to find how many X, how many Y that can maximize profit. So what should we do? We set Px equal to 0. We set Py equal to 0. It is first order conditions maximizing profit, isn't it? Okay. Now from here, let's call this one equation 1. Let's call this one equation 2. From here, we can find X and Y. How do we do it? Do simultaneous equation, subtraction. 1 minus 2, what do we get? 50 minus 60, we get minus 10. Okay? We get minus 10. And then minus 2x minus 2x, we get 0. Minus 2y minus 4y, we get positive 2y. Okay, let me fix it. Positive 2y. Okay, and then set it equal to 0, isn't it? Then from here, you can solve for y. You solve it. I don't show you how to solve it because it's very easy. So y, after you solve it here, some steps, you're going to get y equivalent to 5. From y equivalent to 5, substitute it back here, you can get x. X, you need to show the work here. Here, I just jumped the step. Okay, x here, you get 20. Okay, alright. Now, we need to find discriminant here because we need to check, alright, whether we can have maximum profit or not, or whether it's saddle point or not. Okay, now, of course, we need to proceed. We have found px. Now we need to find pxx. From here, this is our px. That means we differentiate again profit function with respect to x. Second time, what do we get? Minus 2, isn't it? So delta p1 delta x second time, we're gonna get minus 2, isn't it? What about p y y? That means we need to differentiate this profit function with respect to y second time. In this case, we have done the first derivative with respect to y. We differentiate this again with respect to y. We're gonna get minus 4. So here, p2 delta y minus 4, isn't it? We also need to find pxy. That means from here, we need to differentiate with respect to y. Okay, we get this, differentiate it with respect to y, what do we get? Minus 2, isn't it? So we get minus 2. Okay, then using all of this information, we can evaluate or find or calculate the discriminant. So discriminant, like I said earlier, is pxx times pyy minus pxy square. In this case, pxx is minus 2, pyy is minus 4, and then pxy is minus 2 square. What do we get? Here, if you calculate it, you're going to get 4, and it's obviously it is greater than 0. Therefore, we can, we can check whether it's relative maxima or relative minima. It's not a saddle point because d is greater than 0. When d is greater than 0, then we check pxx, we check pyy. You can see clearly pxx is less than 0, minus 2, less than 0. You can see clearly pyy is also less than 0 because it is minus 4, less than 0. So when the second derivative of these two less than 0, that means we have relative maxima. Maxima means maximizing profit. We know that from previous calculation, a quantity of x that can maximize profit is 20. Quantity of y that can maximize profit is 5. Now we need to find profit of x and y. Okay, so profit of x and y is very simple. The formula for profit, the equation for profit that we found is this one. You just need to substitute the value of x and y, x which is 20, y which is 5, into this profit function, and then this is what you get. So it's actually P25, isn't it? Equivalent to 600. Okay. Plus 250 minus 200 equivalent to 650. 50. Okay, I just jumped the step, but you have to show from here, put x and y, x20, y5, show all the steps until you reach this step and this step, then you can get full mark. If you just jump like me like this, then you cannot get full mark. Here I just jump because I know that the calculation is easy. Okay, so here what does it mean, class? We have fulfilled the discriminant, test. This one also we have fulfilled. Then we know that we are maximizing profit when x is 20, y is 5, and the profit that Dell manufacturers can obtain in this case, the maximum one is $650. Okay? But if the answer is saddle point, then we cannot, it becomes indeterminate. We cannot decide. You get what I mean? And if the discriminant is, instead of greater than 0, it is equal to 0, then we cannot also solve it. We need to find the nearest, profit, the nearest quantity that can help us. Which is, most of the time we don't ask when D is less than 0. Okay, so that's the example. More practical example. Move to another different types of optimization, maxima and minima of functions. But this time around, we have constraints. Okay, so because we have constraints, therefore, the optimization in this case, we use Lagrange multipliers. Okay, so we can do this by having, let's say we have a function, the objective function, we call it z as a function of x and y. Okay, so z as a function of x and y. Alright, subject to a constraint, call it gx, equivalent to 0. What does it mean by equivalent to 0? I'll show you in the form of an example after this, then it becomes clearer. Here, I'm showing you the theoretical bit first, then I'll show you using example. Okay, Lagrangian multiplier is basically a name after this person, Joseph Louis Lagrange. So that's why it's called Lagrange multipliers. We can use this objective function. This is what we call objective function of 2 or more variables, when we have constraints, okay, in the equation. Okay, so we have to combine both constraint functions and also objective function into one function. We call it Lagrange multipliers. Okay, so here, how do we do it? So when we combine them, so you have, let's say, fxy, which is here, and then you have the constraint function, which is gxy, and then when you combine it, you put plus lambda. Sometimes I'm also, when I show you example later, I also use minus lambda, instead. I'll show you more in terms of exercise after this. Okay, now once we construct the main objective function that look like this, in which you combine the objective function and also the constraint, so the objective function now becomes unconstrained. Okay, so here what we need to do is, for each of, we have 3 arguments here. The first one is x, the second one is y, the third one is lambda. We need to find x and y that can, optimize this function subject to constraint. So how do we do it? In general, this is what we need to do. Alright, we need to find x, y. Alright, so we need to find 3 different types of partial derivatives and equate them to 0. The first one is delta f over delta x, equate it to 0. Second one is delta f over delta y equal to 0. And the last one is delta f over delta lambda equal to 0. All of this is what we call first order conditions. So this is number 1, number 2, and number 3. Okay, then here how it looks like. So number 1 looks like this. It's basically, the first one here is we differentiate capital F function with respect to x. and then we equate it to 0. So here, first order conditions. Okay. Second one, differentiate f with respect to y. Then we equate it to 0. Then you get something in general like this. Number 3, differentiate f with respect to lambda, the multiplier. Okay, then equate it to 0. So all of these are FOC. Once we have all of this, we rearrange it to find x, to find y, and possibly to find lambda also. But most importantly, we need to find x and y that can optimize this function. Okay, so all of this will give us critical values, and so here, whether it is maximized or minimized, we need to do some, testing. Okay, but here we just learn how to find x and y using Lagrangian multiplier. We are not testing the answer whether it's maximized or not. Okay, alright, so this is what I said just now. This method will not tell us whether the critical points, the x that we calculated, the y that we are calculated, we found, we call it critical points, correspond to maxima or minima. This can be determined either by physical setting for the problem or testing according to procedure similar to the one that we saw earlier. Yeah? Okay, now let's go straight to the example. Let's look at the first example. Minima subject to constraint. Okay, minima subject to constraint. So we have function here, and then we have the constraint here. So write down the Lagrangian function first. So this is the first step, how to write down. Call it capital F as a function of x, y, and lambda, which is basically this one subject to this, isn't it? You see here, we set it equal to 0. Okay, so here, we can also rewrite it this way. I prefer to write it this way: 4 minus x minus y equal to 0. Okay. If we write this way, then we don't have to be concerned so much about the plus minus sign. Okay, so for this. So how do we write the Lagrangian function? So this is how we write it. Write this one first: x cubed plus y cubed plus xy, and then minus. Okay, put lambda, plus. Put lambda, and then in bracket 4 minus x minus y. That's it. Okay, 4 minus x minus y. Okay, now to solve it, we need to find first order condition. First order condition here, we want to minimize. Okay, minimization. Minimize f. Okay, so first order condition we need to do 3 times. The first one is for x, the second one is for y, the third one is for lambda. So let's look how do we do it. Number 1, delta capital F delta x. So it's going to give us, differentiate this, 3x squared, isn't it? If we differentiate y cubed with respect to x, nothing, 0. We differentiate xy with respect to x, we're going to get y. We differentiate the one in the bracket here, but don't forget lambda, multiply. Then we get minus lambda, because minus lambda x, okay, differentiate becomes minus lambda. And then don't forget, equate it to 0, first order condition. Okay, number 2, delta f over delta y. Let me erase this because it looks like gamma. Okay, over delta y. So x cubed we differentiate with respect to y, 0. Y cubed we differentiate it with respect to y, we get 3y squared. Okay, lambda here, this one we differentiate it, we get positive x. Lambda here attached to minus y, differentiate it, we get minus lambda equal to 0. Okay, number 3, differentiate f with respect to lambda. So when we differentiate it here, so become 4 minus x minus y equal to 0. Okay. Alright, now from number 1 we can simplify it further. We get what? 3x squared plus y equal to lambda, isn't it? So I call this number 4. From number 2 we can simplify it further. So we have 3y squared plus x equal to lambda. So I call this number 5. What we can do here is we equate number 4 and 5. Remember, we want to find x and y. Okay, we equate them. So we have 3x squared plus y equal to 3y squared plus x. So this one, I call it number 6. Okay. Now, what we can do with number 3, I forgot to tell you here, rearrange it so that we can have y equal to 4 minus x. So this one, we call it number 7. Okay. So now we have simplified number 1, number 2 becomes number 4 and number 5 respectively. And then we equate number 4 and number 5. We have this. Okay. And then we rearrange number 3. We have number 7 here. So what do we need to do next? Remember, our objective is always to find x and y. So what we can do with number 7 here is to substitute it back into number 6 here. Okay. So you substitute 7 into 6. Okay, when you substitute 7 into 6, so we have what? 3x squared plus y, in which y is 4 minus x, isn't it? Equal to 3y squared, y squared now 4 minus x squared plus x. And then from here you can solve for x equivalent to what? And then you substitute y back into equation, you can get y equivalent to what? In this case, if you try to solve it yourself, I want you to do it on your own here because this is just a matter of calculus. Alright? Now when you solve for x, you're going to get x equivalent to 2, and then you're going to get y equivalent to 2 as well. So these two are the answer for our optimization, Lagrangian optimization. Okay, now let's look at another example. Another example is this one. Example number 4. Find x and y that maximize utility function u equivalent to x squared times y squared, subject to the budget constraint 2x plus 4y equivalent to 40. All of the examples, before I forget, all of the examples here are coming from textbook, but you will see some differences. Okay, because here what I did was, instead of writing plus lambda x plus y minus 4, I wrote this way, 4 minus x minus y, because I just want to get rid of the minus sign here so that there will be less mistake. And furthermore, in economic study, if this one is whatever function, production or utility, whatever, and then minus the constraint, the cost function, actually this is the right way to write it instead of the one in the textbook, to be honest with you. Yeah. Okay, so because the one in the textbook is done differently, because it's just a mathematics rather than full economics. Yeah. Alright, but here I want you to use this way because so that it really have economic meaning. Okay, now of course it gives you the same answer regardless whether you use the textbook or this one, but in terms of theoretical underpinning, this one is precise and correct, to be honest. Okay, now let's go back to example number 4 here, utility function. So we want to maximize utility subject to constraint budget. So for you to understand better, 40 here is considered as income. So 2 here is considered as price of good X. And then 4 here is considered as price of good Y. So X and Y here are considered as quantity of good X, quantity of good Y. Okay, so by knowing this, it's much easier for you to understand the Lagrangian multiplier. Okay, so first we set up the Lagrangian function. How to set up the Lagrangian function? Alright, so here we know that f x y lambda. So we write the objective function x squared y squared, and then we put plus, okay, and then we put lambda. So how do we do this? You see here, we must make sure that we have gxy equivalent to 0. So that means this initial function make it equivalent to 0. So it is written this way, 4t minus 2x minus 4y. Isn't it become 0? Because we fully utilize, income to buy x and y here. Okay, total expenditure. So this one is actually total expenditure. This one is actually income. So whatever being spent must be exactly equal to whatever you have in your hand as an income, because you want to maximize your utility for a given income. Okay, let me delete the mess here. Okay, so now we have lambda, and then in bracket 40 minus 2x minus 4y. Okay, and then we do maximization, maximizing f or cis. Okay, first order condition. So we have how many first order condition? We have x, we have y, we have lambda. We must do 3 times. So that means we have 3 first order condition. Okay, those 3 first order condition. The first one is delta f over delta x. So here you differentiate this, it becomes 2x y square, and then you differentiate lambda and minus 2x, it becomes minus lambda 2. Don't forget to equate it to 0 because maximization process, first order condition. Secondly, delta f over delta y. Differentiate this with respect to y, you get 2x squared y, isn't it? And then plus lambda attached to minus 4y, differentiate becomes lambda 4. Don't forget to equate it to 0. Without equating it to 0 is wrong. Okay, number 3, differentiate f with respect to lambda. What do you get? Only here with lambda, so you're going to have 40 minus 2x minus 4y. Don't forget to equate it to 0. Now, equation 1 here, we can simplify it further by having this 2xy squared equal to lambda 2, isn't it? Simplify it further, 2 over 2 x y squared equal to lambda, isn't it? Then it gives us lambda equivalent to xy squared. So we call this one equation 4. Okay. Similarly, we can do the same simplification of number 2. If you simplify it, I don't show you the method, but you have to show it. Here I just jump into the answer. From here you can get 1/2, isn't it? And then x squared y equivalent to lambda. Or I can also write it this way. Lambda. Don't jump like this, yeah? I just show you the final step, but you have to show me how do you get this lambda. Lambda equal to 1/2 x squared y, isn't it? So I call this one equation number 5. Okay? Once this is done, then we set 4 equal to 5. We can do that. So I'm not following the textbook, the method here, but of course the question comes from textbook. So when you set this equal to this, so what do you have? Xy squared equal to x squared y. Then you simplify it. Once you simplify, okay, want, you're gonna get y equivalent to x over 2. So this one, I call it number 6. Okay, I call it number 6. What can we do with number 6 here? Let me move here. So because we have y equivalent to x over 2 as number 6, then I can substitute this 6 into this. To this, yeah? Into, not this one, sorry. This. Into number 3 to find x and y. Okay, so here, number 6 into number 3. So we know that number 3 looks like this. Let me rewrite it again here. 40 minus 20x minus 4y. So 40 minus 2x, sorry, not 20x, minus 2x minus 4y equals 0. So when we substitute this, so it becomes 40 minus 2x minus 4 times x over 2, 0. Then you solve for x. What is x? What is y? When you solve it, but you have to show the work, yeah? When you solve it, you're going to get x equivalent to 10 and y equivalent to 5. So this x equivalent to 10 and y equivalent to 5 are the combination of x and y that can maximize this utility function given the budget constraint here, given the limited income for T. That's how we do it. Okay? Alright. Now, why don't you try example number 5 here at home? Alright? So this is the objective function. This is the constraint. Remember to write the constraint that look like this, because we want to have g, x, y equal to 0. So we bring it here. So it becomes 100,000 minus 160x minus 200 and y equal to 0, isn't it? Alright, so then you can have Lagrangian function. So here, if you write it, f, x, y, and lambda equivalent to 100x 4/5, power of 4/5, and then times y to the power of 1/5, okay, and then plus lambda, and then in bracket, okay, I write in the bracket here, yeah, because I don't have enough space, 100,000 minus 160x minus 200y, close the bracket. Then you need to find pre-FOC. In this case, we want to, what is that? That maximize production. Maximize, okay, maximization of F, alright, FOCs. Can you do it? Alright, so you need to find how many X, how many Y. In this case, X is how many number of labor, how many Y here is how many capital investment that you need to combine in the production process so that you can produce, okay, goods here with limited cost, which is 1,000. Okay, all right. So I hope you can find it, the answer. All right. So I'll show you more in the class later, inshallah. So with that, I thank you. Assalamualaikum warahmatullahi wabarakatuh.